this is very closely related to the last talk. Uh, so let me start with an example. Suppose we are given points from a distribution independently sampled. Here is a case where I have around 100,000 points sampled from a distribution in dimension 1,000. It's a normal distribution with covariance to be identity, and we want to estimate its mean. Then we will just compute the sample mean. So to make it more difficult, let's say we allow a fraction of the points to be chosen by an adversary. So here I have added around 10% of the points to be chosen by an adversary. And for now, let's say, just as an example, adversary puts all the points in one location. Should be around like square root n, because all the Gaussian points are clustered around that distance. And now if we compare with some of the standard algorithms and our algorithm, this is what we see the performance to be. So the error, when we run our algorithm, which takes around a few seconds, we get like 0.15 as the distance from the true mean. And mean, if we just look at the uncorrupted sample and compute the sample mean, it is like 0.09. And here I compared with coordinate twice median. I think geometric median will also be around the same, will give the same error. Let me define the, okay, so this our algorithm produces a 2D projection where in this case it looks this, like the noise and the Gaussian data are quite far away. So if in a random 2D projection, this is how the thing looks like. The noise is well within the cluster, but we know that since there is some 2D projection where this should be the picture, and at some point in the algorithm we get this picture. Let me define the problem more concretely. So this is the model. We assume there are m points given to us. 1 minus eta fraction of these are sampled independently from an underlying distribution. I'll impose some condition on the distribution later on. And eta fraction are completely arbitrary, can be chosen by an adversary. And the question is to estimate mean and covariance. And we'll consider, we want to estimate mu hat and sigma hat such that it's close to the true mean and the true covariance. The norm with mean we'll use is 2 norm, and for covariance we'll use Frobenius norm. And you can imagine there are many applications to this, because many of the learning problems involve estimating mean and covariance of a distribution. And if you can do it robustly in the presence of agnostic noise, we can give algorithms for those problems too. And the condition we need for our distribution is what's called what we call bounded fourth moments, which means that in any direction v, the fourth moment of the distribution should be less than at most C4 times the second moment square. So we give guarantees in terms of C4, but for this talk we can assume C4 to be a constant. Many distributions satisfy this, like Gaussian, exponential distribution. Any distribution which has a finite fourth moment would satisfy this. So let me state the main results that we give. So suppose the distribution has bounded fourth moments, then we can compute in polynomial time mu hat, which is at most square root eta times sigma times square root log n away. So as you saw in the last talk, most of the computationally tractable methods that exist have a square root n dependence on the dimension. So n is the dimension here. We have a square root log n dependence on the dimension. And the lower bound in this problem has like eta power 3/4 sigma. So we are off slightly in the eta dependence as well. Also, the number of samples we require is like nearly optimal. It's nearly linear in n, roughly n log square n. And if the distribution has a spherical covariance, which means that its covariance is some multiple of identity, then we get the optimal dependence on eta. It's eta power 3/4 sigma square root log n. And in the case of Gaussian, we can do slightly better with, so for a general covariance structure, if we have n square samples, it's more than linear, so we can improve the eta dependence to eta power 3/4. And if we take even more samples, we can get eta power 1 minus epsilon for any epsilon. And for the spherical case, again, we get just for linear number of, almost nearly linear number of samples, we can get optimal eta dependence. But for the Gaussian, like as you saw in the last talk, they get a this kind of bound, probably log 3/2. Okay. So this immediately gives an algorithm for robust estimation of covariance matrix as well. The thing to observe is that if we know the true mean, then covariance is mean of objects of the form x minus mu transpose. So when we have an algorithm which can estimate mean robustly, that also gives an algorithm for estimating means of these objects, x minus mu transpose. And there is a standard trick which avoids knowing what the mean is. So here with n square, nearly n square samples, we can compute a sigma hat in polynomial time, which is at most square root eta log n times the 2 norm of the covariance matrix. We need some additional assumption on the distribution in this case. We need some kind of independence, like it should, I think 8-wise independence, if it is a linear transformation of an 8-wise independent distribution, that's sufficient. And the reason we need independence is to relate the covariance matrix of this covariance matrix of the covariance to the covariance matrix of the distribution. Okay, so in the remaining minutes, I'll give the algorithm and probably sketch the proof. So in 1D case, things are easy. As you've seen earlier, if we have corrupted samples, then median is a good estimate. One thing I should mention is that for the remaining part of the talk, I'll assume the underlying distribution is a Gaussian with spherical covariance. The main part of the algorithm remains same for any distribution. The 1D case differs for distribution with bounded fourth moments, because median is not a good estimate for such distributions, but there is a simple fix for it. So I won't talk about it. I'll just assume the distribution is Gaussian. And then median will have an error of eta sigma. And that's the best we can hope for. And if instead of median, if we look at some other quantile, we can estimate the standard deviation or the variance also up to eta sigma error. Okay, so in higher dimension, okay, this is an example where some standard methods like coordinate-wise median, if you look at median in each of the n coordinates, or geometric median, it will have a square root n dependence. So if you place eta fraction of the noise all at one point in a diagonal position, like in an all ones vector direction, then it's bad, and it will have square root, both these medians will have square root n dependence on the dimension. So also this coordinate-wise median we can give an upper bound that it is like eta sigma square root n. It is not worse than that, because in each coordinate it has an error of eta sigma, so we have n coordinates and it will have eta sigma square root n. So if we just want a square root n dependence, then it is an easy problem. In higher dimension, here is an observation that's kind of is a motivation for our algorithm. If suppose the mean of the Gaussian here is at the center blue dot, and the purple one is the mean of the corrupted sample. That's Gaussian plus noise. So I refer to it as mu s. S is the set of samples. And consider this vector, the direction in which the mean moves because of the noise. So it's a mu(s) minus mu. If someone gave us this direction, the direction in which the mean shifts, then the problem can be reduced to 1D. Why? Because we can consider the n minus 1 dimensional space which is orthogonal to this mean shift direction, and if we project all the points onto this n minus 1 dimensional space, then we know that there is no mean shift because it is orthogonal to this mean shift vector, and just the corrupted sample mean is close to the uncorrupted sample mean. So we have a good estimate for n minus 1 of the coordinates. And in the remaining coordinate, which is in the mean shift direction, it's a 1D problem. We can project all to this dimension, and we can estimate the coordinate by just the median. So then the question is, can we estimate what this mean shift direction is? Probably the first guess would be probably the top principal component of the covariance matrix works. But it's easy to construct examples where this completely fails. Even if we place 2 points far away, we can make that direction to be the top principal component. And we have used only 2 points, and we have eta fraction of points. So we can use them in various other dimensions and completely screw up this top principal component guess. So instead, here is our algorithm. It has two steps essentially. It alternates between a weak outlier removal step, and then it computes the top NO2 principal components and projects onto the top principal NO2 components. Recursively estimates the mean there in the NO2 principal components, top NO2 principal components. And in the bottom NO2 principal components, we can show that the sample mean of the corrupted sample is close to the actual mean. Okay, so let me make that more concrete. So here is the complete algorithm. If dimension is 1 or like constant, we can just estimate it by median or coordinate-wise median. Suppose not, then we consider a ball of radius sigma square root n, order sigma square root n. We can estimate sigma because it's a 1D problem. Variance in every direction for a spherical Gaussian is same, so we can project all to 1D, and like by a quantile estimation, we can estimate sigma. And we consider the coordinate-wise median, which can have an error of up to eta sigma square root n, and consider a large ball around it. Large ball, the radius is like sigma square root n. So in this case, say this is the ball, and we throw away all the points outside it. So these are like really, we can kind of eyeball these outliers and remove it. And once we do that, so say we threw away those outliers, we zoom into it, and then compute the top and bottom NO2 principal components of the covariance matrix of the remaining set of points. Okay, so now we project. Okay, so the mean shift vector is there. The key thing is we project all the points now onto top NO2 eigenspace and recursively estimate the mean there. The reason why this works is because if you look at this mean shift vector, it's mostly along the top NO2 eigenspace. It has very little projection on the bottom NO2 eigenspace. So in the bottom NO2 eigenspace, we can estimate the mean by just looking at the sample mean of the corrupted set of points. So once again, the algorithm is the following. So we are given points, the red points are the noise. We first apply an weak outlier removal step, which is we consider the coordinate-wise median, construct a ball of radius order sigma square root n. Both of these are easy to estimate, and we throw away all the points outside this ball. And in the next step, we compute the top NO2 and bottom NO2 principal components, recursively compute the mean in the top NO2 eigenspace, And in the bottom NO2 eigenspace, we just output the sample mean. And the thing that helps us is that this mean shift vector has a very small projection onto the bottom NO2 eigenspace. And in the remaining few minutes, I'll explain why this is the case. So the thing to do is we write the covariance matrix in terms of the covariance matrix of the Gaussian and the noise part. So here sigma square I is the Gaussian part and sigma n is the covariance matrix of the noise. And then there is this mean shift vector, delta shift delta. That's the mu minus mu s. Sorry, mu s minus mu. And what the weak outlier removal step gives us is that the NO2th eigenvalue, the NO2th eigenvalue is very close. NO2th eigenvalue of the covariance matrix of the corrupted sample is very close to the uncorrupted sample. The noise are all restricted to lie in a ball of radius order sigma square root n after we remove, after we apply the weak outlier removal step. So it just doesn't have enough energy to move all the eigenvalues by much. It can move up to order n eigenvalues. So if we look at the NO2th eigenvalue, NO2th eigenvalue, we can argue that it's very close to sigma square, which is the Gaussian variance. And the reason is because we can control the trace of this noise covariance matrix up to eta sigma square n, and by a standard inequality called Weyls inequality implies that NO2th eigenvalue of the corrupted covariance matrix is sigma square with an error of order eta sigma square. Sigma square is just the Gaussian part. So once we have this, the second step is the following. So this implies the NO2th eigenvalue is close to the Gaussian eigenvalue. That implies that all the eigenvalues below it also are close to Gaussian eigenvalue, which is sigma square. That allows very little room for the projection of the mean shift vector. So that implies that if we look at the mean shift vector, the projection has to be small. Otherwise, if the projection is big, that implies that NO2th eigenvalue is big, but we know that's not the case. So we can bound the projection, the squared projection, by eta square sigma square. And since each iteration we divide the dimension by n over 2, there are log n levels. So we accumulate eta square sigma square error log n times. So we get an error of eta sigma square root log n. And the algorithm is pretty simple. The main routine is just this slide. What I'm hiding is the outlier removal step, but it's also less than this size. So in summary, we give an algorithm for robust estimation of mean and covariance. It works for a wide class of distributions. It just needs to satisfy this bounded fourth moment condition. For mean estimation, we just require nearly linear samples. And it is simple and practical. There are many open questions in this area. So one is, can we estimate the sample mean matching the lower bound? Can we estimate the mean matching the lower bound? So if you recall, there is a gap of eta power 1/4. The lower bound is eta power 3/4, and the one this algorithm achieves is square root eta. Also, can we estimate covariance matrix with a better sample complexity? Now we need n square, but probably in many situations we only order n samples are sufficient. And we can ask for robust estimation problems for in many other learning situations, like say Gaussian mixture models or whatnot. Okay, so thank you. if the outlier are all small in norm, like it's close to 0? Sorry, is the fraction of outliers small, or is I see. So fraction of outliers small is the eta parameter is the fraction of outliers. So the guarantee is when like eta goes to 0, the error goes to 0. Uh-huh. Right, right. Yeah, yeah. No, I don't know that. Like so, in 1D case, in the worst case, we take median to be the estimate, and then we have to incur that much error. It's not in the lower bound. It's probably not essential even for this algorithm, but we couldn't analyze it out. So for it's just the 1D case is different. So in 1D case, instead of looking at the median, which can be very bad for general distributions, even without noise, median may be very bad. What we look at is an interval which contains the smallest interval which contains 1 minus eta fractions of the point, and compute the mean of that.